Hi, we'll talk about our Python code that we use to train a neural network to identify the brainwaves of one user and distinguish them from those of the others. So our goal here is to take user 7 and build a neural network and train it to identify and distinguish user 7's brainwaves from those of the others. Now, before we get into how we train the neural network, let's talk about how we take the files from the file system and create the data and pre-process it to get it ready for a training phase. So, as you can see here, we have a load files function, and basically its objective is to take the indices which correspond to user IDs, and it has a default user ID which is set to 7 since we're training for user 7, and a training ratio which determines the split of the data. So right now it's given at 0.8, which means we take 80% of the data for training and the remaining 20% for testing. Over here we have the ID list. This represents the 14 different kinds of data that the folders of individual users have. We will take all those 14 data points, these files, and combine them into one for every single user because we want to train a model that transcends any differences in any of these sensors. We want to have a model that can recognize a user regardless of which sensor's data we pass it to. Now, we take our target user's data, which is user 7 in this case, and we load all 14 files for user 7 into file 1. We get it ready and we make it into a new NumPy array which takes all that data, which has a total of 66 columns. We dropped the first and last columns because the first column is a timestamp and the last column is just mostly zeros. So that will not help our model to recognize our user. So we will take all the data for our user 7 and we'll add a column which is all ones. The reason for that is we want to have user 7 be classified as label 1 and have every other user be classified as label 0. So here we make a new NumPy array called positive class, and we create a NumPy of ones, and we input our data into it, and we leave out the last column. So you get a NumPy array which has the last column as all ones, which will be their class labels. Now, for the negative files, we create another empty NumPy array, which we will use to get all the other users into. Now, over here, we loop through all the indices, which are basically the user IDs provided to us, and we load them into a NumPy array and a negative class. So what we do is we basically take this NumPy array of zeros and we input our user into this NumPy array, and we keep appending it for every single user. So at the end, you have a very large NumPy array in negative files, which contains all the data of every other user except user 7, our target user, and they have the last column as all zeros, signifying that their class labels are 0. Now, what we do is we look at the size, or rather the number of rows of positive class, and we take a random sample of that many rows from our large negative class file. So now we have an equal split of these samples from the negative class. So this all data has equal numbers of positive class and negative class, and we append it along axis 0. Our next goal is to normalize the data to have every data point be between 0 and 1. As you can see, this normalize is our function that we write here to simply take all the data and normalize it in the range of 0 to 1. Next, what we do is we shuffle the data, because in this append, the first half is all positive, the second half is all negatives, and that can be a problem sometimes for our training process, and the network may not learn the data, as to say, in the best way that we want it to. That's why we shuffle all this data, and next we basically take 80% of the data and put it in trained data, and we take 80% of the data and we put it in test data. And we output this result as a tuple, and the first part is trained data and the second part is test data, and we also save the test data to a file so that we can test it later stages. So now that we know how our pre-processing works, let's go over the structure of the neural network itself. So over here, you can see we have a multi-layer perceptron, and what it does is it basically takes your input tensor, the weights, and the biases, and creates our neural network. We use a ReLU activation function and one hidden layer with 64 neurons. And the output layer has basically 2 neurons corresponding to the 2 classes. So class 0 is trained to be not our target user, which is user 7, and class 1 is trained to be user 7. Now, what we do here is we pass the input tensor and we matrix multiply it with the weights corresponding to the hidden layer 1 and add the biases of hidden layer 1. Once we pass it through the activation function, we take that result and we multiply it with the weights of the output layer, and the biases are then added to it to get our final output layer, which is basically 2 neurons specifying our 2 classes. And now we will talk about how we take our neural network and our pre-processed data and train it for the given data set. So we use 10,000 epochs, and we take that data and we use a Huber loss function because the ranges, even though we have normalized our data, the kind of variability and the ranges that correspond to our data are different. And the best loss function to account for that, according to our tests, has been Huber loss. So we use that as our loss function, and we basically take the mean of the errors and we try to build an optimizer to reduce that mean. And we will be using an atom optimizer with a learning rate of 0.0005, and we will try to minimize our cost. So here we will use the GPU version of TensorFlow because our data set is really large and computing matrices of this size is not really feasible on the CPU given the time that we have. So there are some optimizations that we will be doing here. So the first optimization is that we're using an NVIDIA Tesla GPU, which has 24 gigabytes of storage in the VRAM. So to take advantage of that fact, we take our entire data set and we create a TensorFlow constant. The reason we do that is once you create this TensorFlow constant, since our session is based off of the GPU, this constant will be stored on the GPU's VRAM itself. So there will be very little traffic across the buses, which will significantly improve our performance. Now, we run through all the epochs and we get the errors of each epoch and we display it as we run it. And we look for convergence at a point where we see that, basically the error is not going down anymore. So we stop it at that point. And we take that correct predictions, and the result is basically the output of the neural network is basically 2 values, and the larger of that value is the node that the neural network is classifying. So to account for that, we do an argmax, which basically takes the 2 values and gives you the index 0 or 1 according to whichever value is larger. So if the value for node 0 is larger than the value of node 1, we can say that the neural network has classified that particular data as being node 0, which means it is not user 7. Conversely, if the value for neuron 1 is more than that of 0, that means that the neural network has classified it as label 1, which means it says that the given data corresponds to user 7. So we save our results, we save the model, we save the data for future testing, and we run this over time, and we keep tweaking our training epochs until we get a convergence and a learning rate that we are satisfied with.